Assalamualaikum warahmatullahi wabarakatuh. To our lecturer, Dr. Zakir, my name is Fatin Nabila binti Muhammad Jamal and I'm going to present my part low pass filter for our microwave passive filter project. So this is my part low pass filter. So I have to design maximally flat low pass filter with cut-off frequency of 2.3 GHz and 43 dB insertion loss at 6.6 GHz. There are two types of design that are low pass filter using lump element LC, inductor and capacitor. And the second design low pass filter distributed transmission line design. So the third point is it is a substrate specification that we will use when we design for distributed transmission line. Okay, next. So this is the calculation for low pass filter using lump element LC. So based on the specification earlier, so this is as we know is F, and this one is FC, cut-off frequency. So we can find omega and omega C. And then this is the formula for normalized frequency that we will use here in this table, figure 8.26. That you can get this table from POSA, David and POSA. So we get the value 1.9, and as we know from the specification earlier that the insertion loss is 43 dB. So here 43 dB and normalized frequency 1.9. We can see that the order n is 5, less than 5, almost to 5. So we take n equal to 5. So we look at the table 8.3 for maximally flat low pass filter prototype. So this is the value of low pass filter, and then we use pi combination circuit to design maximally low pass filter, maximally flat low pass filter using the conversion below. So I show you next slide. So for example, so this is pi circuit. So to get this value, we have to insert the value of G. For example, that one is C1, right? It's capacitor. So we use C1. We substitute this C1, G1 over RO is for 50 ohm, and then we get the value of WC 2 pi times 2.3 GHz, and then we will obtain the value 0.855 picofarad. And for inductor here, so we will substitute this formula. So for inductor is G2 times with 50 ohm over this WC, and then we get the value of G2, and so on. And then we can simulate using S parameter. We put the start is 1.0 GHz, stop 7 GHz, and step is 100 MHz. Then we get frequency response. So negative 3 dB is where the signal is accepted. This is a pass band. The wanted signal. Next, we'll move on to second design. Calculation for low pass filter distributed transmission line design. So this is the first step, that is Richard transformation. When we want to turn it to transmission line element. L will become series stub. I have list down G2, G4, and capacitor will become parallel stub. And then conversion formula for L, just take the G value, and for capacitor, take the 1 over G, calculate 1 over G, 1 over G1 for example, and then we get the result like this after Richard transformation. Next is step 2, Kuroda implementation. So in Kuroda implementation, we have to remember this. This is the key to calculate, to implement Kuroda. Okay, so for Kuroda implementation, so first we add transmission line. As we seen earlier at Richard transformation, there are no 1 here. So we add 1 here. We introduce new transmission line. At transmission line both end with value of normalized impedance equal to 1. And then we separate, we calculate the portion, 2 portion here. So as we can see here, this is transmission line. So transmission line followed by shunt stub. So we calculate like this. And shunt stub followed by transmission line, we calculate like this. And then we get the series stub. So we do more. After we change the shunt stub and transmission line become this that we get earlier for both of this. Then we calculate, we separate to 4 portion, and then we calculate again. Then we get the normalized impedance for different stub. So this is the normalized impedance for different stub, and we denormalize it with 50 ohm impedance. So we will produce the layout design like this, and we will use this to do our design in ADS. The simulation using ADS. This is what we have done. So we have to, as you can see here, this is the M-lin, M-block. If you notice 1, 2, 3, 4, 5, this 5 represent the 1, 2, 3, 4, 5. Represent this stub. And 1, 2, 3, 4 represent the M-lin. Line calculation. We have to input the M substrate. So M substrate is this value. We need to put to the M-lin, and then we need to change the ZO according to the theoretical layout that we have designed using calculation. And then frequency 2.3 GHz for each of the stub, the electrical 45 degree for each stub, and then only transmission line is 90 degree. Then for each stub we will synthesize, and then we will input the length, each of the length. After that we can simulate using S parameter. The frequency, we get the low pass filter. There is a shape but it is not tuned, so it is almost negative 3 dB, but we get the frequency at the 2.3 GHz. But the later frequency we did not get. insertion loss at at 6.6 gigahertz. And the shape is, you can see the shape is there. The shape is shape of low pass filter. Next, for to generate the layout, we have to add P1 and P2. So here we add P1 and this end we add P2. When we add them, we can generate the layout design. So this is the generated layout design for low pass filter distributed transmission line using ADS software. So that's all for my part. Thank you.
Assalamualaikum warahmatullahi wabarakatuh to Mr. Zaki. First of all, I'd like to introduce myself. My name is Fakaruddin Arazi bin Zulkifli. Today I will talk about Microsoft passive filter project. So specification for band pass filter. So we are using 2.3 GHz cut-off frequency, 250 MHz bandwidth, and maximally flat rate and n equal to 5. So we can find the low cut-off frequency. Formula is cut-off frequency minus bandwidth divided by 2, and we can find which is 2.175 GHz. So for the upper cut-off frequency, the formula is same, but we are using plus signs, and we can find the value is 2.525 GHz. So we need to find the fractional bandwidth using formula omega 2 minus omega 1 divided by omega 0, and we can find value is 0.1087. So there are two types of compensation formula, which is for shunt capacitor and series inductor. So using the formula, so the first one is shunt capacitor. We are using the formula shunt capacitor. We can find the inductor one is 0.909 nanohenry, and capacitor one is 7.868 picofarad. So the next one is series inductor. So we need to use the formula for series inductor. So for inductor 2, can use GK multiplied by RO divided by fractional bandwidth multiplied omega 0. We can find the value is 5.1.5 nanohenry. For capacitor 2 is 0.093 picofarad. So for the shunt capacitor 3, so in that the value is 0.188 nanohenry, and capacitor 3 is 225.464 picofarad. So basically the value for series inductor L2 are same with series inductor L4, and series capacitor 1 is same with the shunt capacitor C5 because the value of element is same. So this is my prototype for band pass filter. As you can see, this is a shunt capacitor, this one is series inductor. So there are total 5 elements in this circuit. So I'm using advanced design system. We can plot the graph. So basically this is lower cut-off frequency M2, M1 sorry, M2 is upper cut-off frequency. So that's all for me. Thank you. Assalamualaikum.